Hi, everybody. Welcome back. Before we introduce our next speaker, I just wanted to announce that we'll be starting to call for speakers for our 2015 events. We'll be having Seattle in May, New York in March, and San Francisco in November again. So we'll be calling soon on Twitter and other avenues and email that we'll be looking for speakers for our next round of events. Now I'd like to introduce Kwok Lee of Google Brain, who will discuss sequence learning of natural language understanding. Thank you.
Good afternoon, everyone. Is the microphone doing okay? Okay. So good afternoon, everyone. My name is Kwok Lee. I'm a software engineer at the Google Brain project. I have been working at the Google Brain project for almost 4 years. I was there, started the project. I have a passion for building intelligent machines. I think it would be greatly useful if we can have a machine that can see, can hear, and can talk and communicate with us. I think that would be very useful. And since joining Google Brain 4 years ago, we made great advances in a lot of these areas. In particular, something like object recognition. Last year, Google participated in the ImageNet challenge, and the performance is that we are almost as good as a human expert for object recognition, something that I think that unbelievable. But there's something else that extremely hard for machines right now is in the area of natural language understanding. I think having a machine that can understand language well would be very, very useful. For example, right now, search engines still can't answer long and complex queries. We're still very far from having a machine that can have a simple conversation with humans, right? Or if we have a simple application like let's watch the videos from the morning till now and give a summary of all the key points of the talks, we're still very far from it. For that to happen, we need machines that can listen to the audio, but also even harder is comprehend the natural language in the talks. And that's the area that I've been actively working on in the past few years. It turns out that if you look deeply into a lot of natural language problems, it's kind of problems that are very hard for the current paradigms in machine learning. So the success of machine learning, the current machine learning paradigm is the following. It's trying to map fixed length input, some kind of vector, and then trying to map it into some scalar label. So for example, you look at an image, 200 by 200 pixel, trying to categorize whether that's a cat image, right? Or you're trying to look at some pieces of speech and trying to categorize that, what the person was trying to say, maybe the word cat. So the success is mapping a fixed length vector to a scalar. But if you think about natural language is beyond a fixed length vector and a scalar. Natural input, if you think about question answering, would be the question, and the answer is the output. And the input is a variable length sequence, and the output is a variable length sequence. Right? If you think about machine translation, then the source sentence is a variable length sequence, and the target is also a variable length sequence. And this goes on and on in natural language, right? This is the area that machine learning hasn't made a lot of success so far. So for example, I give an example here. This is the example, I love music, and that's a variable length sequence, and the variable length sequence in French for machine translation. Now, let's take an example of how people would use machine learning to solve machine translation today. Right? So because it's variable size sequences, right, then people what would do is that they're trying to translate one word at a time. For example, I go to school, you try to translate I to French, go to French, to French, school to French, right? And then maybe you try to have some kind of language model to reorder all these words so that the sentence make sense grammatically in French, right? And then you use some sort of machine learning for the language model to put the words together, right? But then there's a bunch of hand engineered rules that you have to deal with. For example, if you say New York, then you don't have you have to translate New York as a phrase rather than New and York, right? And then the meaning of the word would depend on the context. So you come up with like rules and one after the other. So if you work on machine translation, for example, then you end up with a table of rules about like 100 rules, right? And no engineer that I know of would be able to comprehend all these rules or rewrite all these rules in a computer program anymore. And we want to go beyond that. And if you take machine translation as one example, what about question answering? What about some other things in natural language, right? Having a conversation. Then you have to hardcode all these rules. So it doesn't seem too scalable. And we want to be better than that. Now, it turns out that we recently developed a very simple solution. This work we're going to be reported at MNIST, and I think it's a very fascinating result. So the idea is very simple. You have a sequence input. You use something called a recurrent neural network to encode the sentence into a fixed length vector, right? And then you have that encoder vector, and then you start generating one word at a time using another recurrent neural network to generate the output sequence. So let me give you a more concrete picture of that. This picture looks like this. So let's suppose that I want to map sequence ABC to WXYZ, right? So ABC could be a sentence in English, and WXYZ is a sentence in French, or ABC is a sequence of words in a question. WXYZ is a sentence of words for the answer. Now, here what you do, you use something called a recurrent neural network. It reads A into a vector. That vector will be the input for the next stage, right? And the next stage will take B as the input as well. And all the horizontal parameters are the same, and all the vertical parameters are the same. So it will read ABC until it reads the end of sequence symbol into a hidden stage. and then it will start predicting. It will start predicting, ideally, it will try to start predicting, W, and then you take W and feed back into the input, and then you keep predicting. And you keep predicting until you hit the end of sequence symbol. Right? So during training, this is what you do. You eat all the sequences, you take the ground truth, and then you feed back into as input to the generator. Now at test time, what you don't have at test time, you don't have the ground truth. So what you do is you take what you predict and feed back into the loop. Right? So and in the generator, let's suppose that I predict the first word, then I take the first word as the candidate and feed back into as input for the network. Right? And the network keeps generating. And until it sees the word EOS, it will stop predicting. Right? Now you can do something even better. So at every stage, you're predicting using a softmax. So you can predict several candidates. So you take the top 5 candidates as input for the next stage. And the 5 will be fed into the network again to generate like 25. 25 put in the network, you will generate even more. So we call that the beam search. So it will generate many sequences after several steps. But you truncate using the log likelihood. So you only keep the candidates that have very high likelihood. And the outcome is you can generate sequences very nicely. Machine translation, I always get back to machine translation because it's a set of benchmarks that people have done so many times in the past. And it's known to be really hard to make even 1% improvement in machine translation. Right? And but it's like this kind of solution, because it's so general, it should not be limited to machine translation. But here's the result. So we train our model on a dataset called WMT dataset. It's quite small, but it's a very reliable benchmark. Lots of people in the world worked on it. People worked on many years. The state of the art is a system that combines maybe 10 methods or so. And each of these methods took many years, human years to develop. And in total, I would guess, about 20 years of work going into that state of art. And this is only working for machine translation, by the way. Their solution only working for machine translation. We took this general solution from deep learning that hopefully can work for QA and all the things. And then we, 3 of us, Ilya Suskava, Oreo, Vignette, and myself worked on this problem for like a year or so. And we make the same performance with the state of art. And I think if in a couple of years, I think the result would be so much better. But I think what's fascinating is having a simple solution and general solution and apply to a very specific problem, you can still be as good as something that's been engineered for many years. Okay, so let's we can visualize what's going on in the network. So let me go back and say what it means to visualize. So the network has 2 components into it: the encoder, which is the left half of the network, and the generator, which is the right half of the network. Right. So as soon as we read the EOS symbol, which is the end of sequence symbol, to the hidden state, that hidden state would be responsible for remembering how going on inside inside the sentence already. And we can take that vector over there as a representation for your sentence. And then we can visualize it in space. Hopefully by using some kind of PCA to project it down to like 2 or 3 dimensions or so. And here's how, and we visualize a couple of examples. So we fed in sentences like Mary admires John, Mary is in love with John, Mary respects John, John admires Mary, John is in love with Mary, John respects Mary. Okay, now why I'm doing this? So the standard representation for sentences usually use back-upwards representation. Back-upward representation doesn't care about the order of the words. So John loves Mary is equal to Mary loves John, which is silly, right? But that's the state of art, that's what we have. And here's a representation show you that our encoder does a much better job. So John admires Mary is closer to John is in love with Mary and closer to John respect Mary than Mary admires John. So it starts to understand the meaning of the words and the order of the words. So I think that's pretty nice. One thing. So here's another example. I was given a card by her in the garden. It's closer to in the garden. She gave me a card, and further away than she was given a card by me in the garden. So it understands who's the person that performs the action and the person who receives. This is I think is a big step in understanding language. So we've been applying these techniques to many problems. For example, question answering, speech recognition, machine translation, and so on. And we have a lot of good success there. So this talk, I want to narrow down to machine translation so that you understand what's going on. But we published this paper at MNIST. It's called Sequence-to-Sequence Learning with Neural Networks. And the idea is very simple. The network was able to read in the sequence and generate the output sequence. And I think what counterintuitive about this approach, I want to emphasize again, is to many people, the ability to read a very long variable size sequence into a vector, a fixed length vector, is very counterintuitive. Let's suppose that I have 20 words, I also represent as a vector, but I also have 10 words, I also represent as a vector. And that's counterintuitive to many people. But the fact that it works out is I think, surprises many of us in the deep learning community. I will stop